Hello everyone, welcome to lecture 4 and today I will talk about some function that we have in the Numpy and this function can be useful for accessing data or manipulating data in the Numpy array. Before that, I want to talk about some reminders and the assignment 2 will be released today, and then you need to choose dataset that you want to work on that in the project. The dataset can be in your research area, or you can choose dataset from online publicly available data on the web, but you need to submit a short description of the dataset by assignment 2. And the deadline for the assignment 2 is the next Sunday. And same as the first assignment, you will be graded by AutoGrader, and your grade will be exactly what the AutoGrader gives you. And I am happy to answer Piazza posts and emails, and you can come to the office hour and take meetings to discuss about the problems that we have in assignment 2. But you need to start early enough to ask questions about the assignment 2. So let's start the today lectures, and at the first I want to talk about the indexing in the Numpy array. And if you want to access a single element in the Numpy array, you can do it with providing an index for each dimension and separated by comma. For example, if you have a 2-dimensional array and you want to access one element, you have to input the first index, which is the row, and the second index, which is column, and then access it by these two numbers. So, for example, here we have a one-dimensional array, which is the np.arrange6, and this can return a list or one-dimensional array that starts from 0 until 5. So if you want to know what is the value of the fifth index or fifth numbers that you have in this one-dimensional array, you can use a square bracket and then 5, and there you go. You can have the value of this index in this array. And also you can access the value of one element in 2-dimensional array. For example, here B is a 2-dimensional array, which is a diagonal matrix, and the value of the value of the elements in the diagonal is 1, 0, 1, 2, which we pass to this function from the Numpy, which returns a diagonal matrix, and then you should pass the value of the numbers in the diagonal. So after defining that, B is a 2-dimensional array, and if you want to know what is the element in, for example, row 2 and column 2, you can separate it by commas, and then you can access to one element in 2-dimensional array by this. So after that, if you want to access multiple entries, you can you can use the colon notation, and then also this is called slicing, which is kind of slice the matrix or the array that you have in the Numpy and get some numbers that you have in that the Numpy array. So for example, here, we define A as an np.arrange, which give us a one-dimensional array, start from 0 until 9. And we want to know the element that we have in this list start from index 1 until the index 9 steps, and the step size can be 2. So for example, here we use colon and we mention the start index and the end index and the step size that we want to have in the output. So for example, here we mentioned the first index should be 1 and until the index 9, and we want to have the output by step size 2. So we get, as output, we get a 1 and then 3 and then 5 and then 7. Note that the end index is not inclusive, and so same thing happens when we have a two-dimensional array. For example, here we define an B as a two-dimensional array, and we want to know all elements that we have in the second row. So we can do that by passing the one as a first index, which is a row that we want to have, and then we can pass all elements that we have in all columns. For example, here by just mentioning column without any numbers. For example, here we can have 0, 1, 2, 3. But if you don't put any numbers here and just column, means that you want to know all the columns in the matrix. So as you can see, the output is just the second row, because we mentioned that the first row, the index for the first row is 0, and the index for the second row is 1, right? So if we mention that we want first row and we have comma and the column, we get all the elements that we have in all columns in the second row as output. So if you want to have all some elements or multiple entries, you can use column, and this is how we can control the index that we want in one dimension. We can have a start and we can have end and the step size. So let's see an example in 3 dimensions. And as you know, np.ones give us a numpy array that all elements in the numpy array are ones. And by passing shapes or the size of dimension, we say that, okay, we want a 3-dimensional array. The size of each element is 5, and then we get the 3-dimensional array and all elements are 1. So if we want to have access to multiple entries, or for example, a row or column, how we can do that? So if we want to know that all numbers that we have in the second row, you can pass 1 as a first index, which is the row, and for the second index, we pass column, means that we want all elements that we have in all the columns. And also for the depth or stack, also we pass column. So this can give us all elements or numbers that we have in the second row, and all columns and all depths. Same thing happens when you change the the index here. For example, we have all the rows, and then we want to know the all numbers that we have in third column, because the first column, the index for the first column is 0, the second column is 1, and the third column is 2. So we mentioned that we need all the elements that we have in the third column and all rows and all depths. This is how we can access the elements that we have in the NumPy array. And you can put numbers for depths and then columns, and you can get the numbers that you have in, for example, in all rows, in all rows for the fifth column and then third depths. Also, you can include the step size, as I mentioned here, because after the first column, if you have a second column, means that you want to have a step size for accessing elements in the metric. So here we said that, okay, I want all elements in all rows by step size 2. This can start from the first row and until the end of the end row, and by step size 2. For the columns, we mentioned that start from the second column until the end, and step size can be considered as 2 for the column also. And all that we have for the depths are just for the first depth, not other depths. So this can give us these numbers that we have in three-dimensional array. So in this way, you can access to each elements or each row, each column, everything that you have in the NumPy array. And so one thing that you also notice until now is that if we want to pass a single index for a dimension, the result will have one fewer dimension than the original array. For example, here we have A, which is a three-dimensional array with this size for each dimension, 2, 3, 4. And we pass for the column one index, which is 1. And then we get the shape of the output. And then you can see we get the one fewer dimension for the output, which is 2 and 4. And in this case, we just get the second column, and all rows and all depths or stack for the output. So this is obvious that if you want to know that what are the numbers in the second column, so you just get one two-dimensional array instead of three-dimensional array, because you just have one column. So if you pass a single index for a dimension, obviously the result will have fewer dimension, one fewer dimension than the original one. And so after accessing two elements or numbers that we have in three-dimension or the ND dimension array, if we want to change one element, if we want to assign an individual array interest to or slice, we can do that by indexing. So for example, here, we want to have an array two-dimensional array with size 3 and 3. And we want to assign a value for the elements that we have in the third row and the second column, and assign the value for that elements to 9 instead of 1. So the output is like this. All the elements are 1, and then for this entry, which is this is the first row, second row, and third row. For the first column and the second column, which is here, and we assign a value 9 for that. You can do that. This is a single element that we want to assign a value for that, right? So if you want to assign a value for all, not all, and some index in the array. For example, here we want to assign a value for all the elements that we have in the first column, right? So we can do that by passing 0 to the column index, and then column index, and then we have the column in the first index, which means that for all the rows that we have in the one-dimensional array, we can pass 5 for that. So after that, you can see that all numbers in the first column are 5. So also the shape of two sides of this assignment is so important. For example, if you want to assign a value for all the column, all the members that you have in the first column, you can do that by this column, this line, right? But consider that you want to, for example, assign the first row by 1, 0, 1, 2. How we can do that? So because the value of each element is not same, the first should be 0, the second can be 1, and the third is 2. So we can do that by calling and assigning a value for the first row after A, and the np.arrange can give us a 1D dimensional arrays start from 0 until 2, right? So the shape of this is 3, and also the shape of this also is 3. So we assign the value of the first row by the one-dimensional array here, and then we can have the np.arrange 3 as a first row of the this A, which is the np.numpy array. So for NumPy array, we have some shapes for the first or second or third dimension. And sometimes we need to reshape the size of the dimension that we have. So NumPy provides some function for changing the shape and size of an array. But the most basic is the reshape, which will return an array with a new shape. So let's see an example. For example, here we have A, which is a one-dimensional array, start from 1 until A. And we want to generate another array, which is two-dimensional array. And the size of each dimension is 3. So we can do that by calling a function for the A, which is the reshape, and passing the size of dimension that we need to have in the output. Note that the size of the output of reshape should be same as the size of that we have in the A. For example, here we have 9 elements, and then if we want to generate another array with size of 3 and 3, we can do that because if we can have two-dimensional array with 3 rows and 3 columns, the numbers that we have are same as the first one-dimensional array that we had. And also you can do that same thing with passing, with assigning the shape of the array by 3 and 3 like this, and the output is the same as previous output that we had. So note that the reshape is a function for this one-dimensional array, and also shape is an attribute of the A that we define here. So if we change this attribute of A to 3 and 3, we get the two-dimensional array, and the size of rows, the row, we have 3 rows and 3 columns here, right? So we can do that with reshape or changing the attribute of array, which is shape. So another example that we have here for the reshape, we define x as np.1s and 10, and we want to generate a two-dimensional array, and we call reshape function here and pass the dimension that we need to have in the output. So we want 2 rows and 5 columns. So the Python can give us for the first row from 0 until 4, and then for the second row we have 5 and until 9. If you want to have 5 rows and 2 columns, so we start from the first index and generate this first row, and then second row and third row until the last one. So note that the size of the output is the same as the first array that we have. For example, here we have 10 numbers, and we should have 10 numbers in these two array that we generate based on the first one. So Python allows you to specify a single unknown dimension using -1. This means that sometimes you don't know, or you don't want to worry about the second dimension or third dimension. You just want to have for example, 2 rows. So if you have a one-dimensional array, start from 0 until 5, and then you need to have a two-dimensional array with 2 rows, but you don't care about this rows that you don't care about the number of columns that you have in the output. You can pass -1, and then Python automatically generate this the number of columns based on the 6 or 2, and then divided 6 by 2 and see what is the -1. So if you pass -1 means that the Python can generate the exact numbers automatically by these numbers. So for example, for this one, we want to have in the output 2 columns, but we don't care about the number of rows that we have in the output. So we just pass -1. Other useful function, return specific shapes. For example, Ravel can flat your NumPy array, and this means that if you pass a 2-dimensional array, for example, here A is a 2-dimensional array or 3-dimensional array, and you want to generate a 1-dimensional array, flat array, you just need to call Ravel parentheses, and the output is just 1-dimensional. And if you want to transpose your array, you can call a function for the array, which is a.transpose parentheses. And also you can use a.t instead of calling transpose. And this means that we want to change the column and the rows and get the transpose of the matrix. So there is a fancy indexing in the Python NumPy array, and honestly, I don't use this fancy indexing in my code or in my research, but let's see some example of that in case you are interested in that. So arrays can be indexing using other integer arrays. It means that until now we just pass numbers as an index in NumPy array, right? So for example, let's see an example here. We pass, for example, 2, 1 as an index for the NumPy array, but we can also pass other integer arrays as an index for another array that we have. For example, here we have A, which is the NumPy array, start from 0 until 9, and another because we multiply by 2. And we want to know the index in these the value of the elements in this index, right? So instead of mentioning them one by one, we can define another array, another integer array, which is B here, and then pass B to the index for the second array. So we get the value of the index in the 1, 4, 5, 7, and then value of them are appeared here. And this can be useful because instead of calling the A, for example, for the index 1, index 4, index 5, you can pass an array to the A and get all elements just by one calling. And this can be also applied for the 2-dimensional array. And for example, here we define A by np.arrange and then reshape that by 2 and 3, because this can return 1-dimensional array when we want to have a 2-dimensional array. So we reshape that by 2 and 3. And the output is the 1, 0, 1, 2, 3, 4, 5, and 2 rows and 3 columns. So if we want to access to first row and the second column, right? We can have two array in two integer array. For example, here B which is a one-dimensional array, 0, 0, 1, and C as a column that we want, and 1, 2, 2, and then pass B as a rows and C as a column. So the output is one by one. We can consider that one by one, and the output is elements in the first row in the second column. So first row, second column is 1, right? So we can have 1 in the output. So for first row and then third column, first row and third column is a 2, and then we have 2 in the output. And then second row and third column, which is second row and third column, which is 5, and then we have in the output. So instead of just mentioning each element y bar 1, we can do that by passing other integer arrays to another array and get the output. So broadcasting also is an important in the Python and Numpy. And let's see what's the broadcasting. So in most cases, when the shape of two arrays does not match, right? For example, we have an array which the size of array is 2 and 3, and the second one is 3, 4. So the shape of two arrays that don't match here, and then Numpy will not let you perform elements operation between them. For example, if you want to have elements multiplication between two arrays, that the first array is 2 by 3, and the second one is 3 by 4. We cannot do that because we don't have same numbers in two arrays. So in most cases, NumPy will not let you do that. For example, here we have A, which is a NumPy array, two-dimensional array, and we generate another array by np.arrange5, and A is a two-dimensional array, 2 by 3, and B is a one-dimensional array, 1 by 5, and we cannot do element-wise multiplication between them. So we get the error that operands could not be broadcast together with shapes 2 by 3 and 5. So in most cases, we cannot do that. We should have same size in both side of the operation that we need to do that. But in some special cases, NumPy will replicate one or more of the inputs so that it can perform the desired operation. So this is called broadcasting. If the NumPy replicate the array that we have to do an operation, means that the NumPy broadcast the array to make it feasible to do an operation on two arrays that the size of them are not matched. So for example, here, we generate A, same as previous example, by the shape size 2 and 3. And also we generate B, which is a one-dimensional array, and the size of the array is 3, right? So in this case, if we have element-wise multiplication between A and B, that can be done by broadcasting. Means that the then the NumPy generate another row for the B and try to multiply element-wise multiplication between two numbers in each array that we have here. So we have A, which has 2 rows and 3 columns, but we have B, which has 3 columns. So the NumPy generate another row for the B and then try to make the B to have 2 rows and 3 columns. And then we have element-wise multiplication between them. So here we have, for the B, we have 0, 1, 2, right? So if we want to have element-wise multiplication between them, the NumPy generate 0, 1, 2, and then another row 0, 1, 2, and then try to generate the output by multiply each element. So for the first one, we get 0 multiplied by 0, which is 0 output. And for the second one, we get a 1 because in the first row of the B, we have 1 also in the second column. And also we can have 2 multiplied by 2, which is the third column in the first row of the B. And then in the second row, we also have again for the B 0, 1, 2. So we multiply 3 by 0 and 4 by 1 as output and 5 by 2 as an output, which is 10. Let's see an example by a figure here to make sure that everything is clear. So here we have X, which is a two-dimensional array with size 5 by 2 by 3, and we have 5 rows here and 3 columns. And we generate another one, which is Y, and the Y has just 1 row and 3 columns. So if we want to, for example, add X to the Y, we cannot do that because how we can do that? Because we have just 1 row for the Y, and we don't know what we can do for the second row in the X. So the broadcasting means that the NumPy generate other rows for the Y and then try to add each element-wise in X and the Y. So this means that we just replicate this first row in the Y 4 times to generate a two-dimensional matrix to make it feasible to add 2 matrices. This is the broadcasting, and also you can see an example here for the multiplication. But consider that the difference between this example that we cannot do that by this example that we can do that is the size of the column, and at least one size is the same. For example, here the size of the B here is same as number of columns that we have for the A, right? But here the number of rows that we have for the A is 2 and the number of columns is 3, and the size of B is 5. We cannot do broadcasting for this because the size of B doesn't match for rows or columns in the A. So by mentioning some special cases here in these slides, I mean that at least we should have we should satisfy some constraint to use the broadcasting in the NumPy. Here we have the same size for the B, same as the number of columns that we have in the A. to make it feasible to do the broadcasting. So another topic that we want to talk in this lecture is the reductions. And reduction is so useful in the NumPy because sometimes you need to add some elements in the array. Sometimes you need to generate a statistic between some arrays, some elements, some numbers in the array, and then reduction can be so helpful in these cases. For example, if you have a two-dimensional array here as a, and you want to know that the sum over all the numbers that you have in this array. So you just need to call a function for the NumPy array, which is a sum, and get the sum over all the numbers that you have in the array. So this is a kind of reduction because we have 6 numbers here and we just want 1 numbers as a summation. So that's why we call it reduction. And most reductions take an argument access which allow you to specify the dimension that you want to aggregation take places in that dimension. For example, for the two-dimensional array, we have axis 0 and axis 1, and axis 0 can be considered as a row, and axis 1 can be considered as a column. And for example, if we call some function here, x.sum, and we pass access to as a 0 to this function, means that you want to get the summation over all the rows that you have. So as you can see, if you assign axis 0 in summation function, you will get a summation over all the rows that you have for each column. And the output is the shape of the output is the number of columns that you have. And for each column, you have a summation over all the rows. You can pass axis as a 1 to the summation function and get the summation over all numbers that you have in one row. And so in this case, the size of output is the number of rows, and for each rows, we get the summation over all numbers in all columns. So this is a kind of reduction in the NumPy array. And other common reduction are product, or for example, here we have an example of the product in NumPy array, and we have a two-dimension array, and the size of them are 3 by 2, and then we want to get the product of them, and we pass access as a 1, and then we get the output, which is the number of rows for that we have in the A, and then multiplication between them, which for the first row is 1, which is for the first row is 0, 1. For the second row is 2, 3, and the second and third row is 4 and 5. So if we multiply the two numbers that we have in the first row is 0, 1, the output is 0, and then for the second one it's 2 by 3, which is 6, and then finally we have 4, 5, which is 20. you can get the maximum number that you have in each axis. For example, here we pass axis 1, and which means that we want to know the maximum number that we have in each row. So for the first row is 1, and then for second row is 2 and 3, which is 3. And then for the third row, we have 4 and 5, which is 5. Also, obviously, you can change max to min to find the minimum value that you have in each row or each column. So also, if you want to, sometimes you want to know the value of the maximum or minimum value that you have in one row or one column. Sometimes you want to know what is the index of the maximum value. So, for example, you can use argmax, and this can return the index value of the maximum value in each row. So for the first row, we have 1, 0, and 1. So 1 is the maximum, and the index of the 1 is 1. So we, as output, we have 1 also. For the second row, we have 2 and 3, and 3 is the maximum. So same as the first one, we get a 1. And then for the third row, we have 4 and 5, and 5 is the maximum, and then the index that is 1. Also, you can get the minimum over the numbers that you have in a row or column by passing axes, and then we can get the output. For example, for the first row is a 0 and 1, and then the mean of the 0 and 1 is a 0.5, and then so on. You can also use a standard deviation or something like this, and we have lots of functions in the NumPy array that we can use to generate a desired output, but also you can note that we pass the axis to the -1 here. This means that -1 corresponds to the last dimension, because if the first dimension, if the index of the first dimension is 0, so the index for the last dimension can be 5, 4, 5, like this. But if you don't know what is the index for last element, you can just pass -1 to that. And also NumPy has some other function that you can use. For example, NumPy has a median function. You can use this function by just calling np.median and then pass the matrix that you want to compute this statistic on that, and then pass axis as another parameter to the function. So the syntax is a little bit different with the previous function that we saw. For example, here we just call some function from the same array that we are working on. That, for example, a.st. But also you can use np dot some function, for example, np.median, np.mean, or something like this. But in this case, you need to pass the array and then access to generate the output. So stacking, another topic that we talked today. We finished about the reduction, and now we want to talk about the stacking. And then NumPy provides a number of functions for combining arrays. For example, you have 2 arrays, and same thing for both of them. They are np.1s 3 by 4 and another 3 by 4s np.1. And we want to stack them to combine them vertically. So if we want to do that, we can call a function for the numpy, which is np.restack, and then pass two arrays that we want to have in the output. So the numpy get a, and then concatenate the second arrays that we have here to the first one. So if we want to know the shape of this, we have 6 rows and 4 columns because we combine them vertically. And if you want to have if you want to combine them horizontally, you can use np.hstack, and this means that we have same rows in the output for A and B. Here we can see 3 rows, but we combine the columns. We have 4 columns for the A at the first, and then we have another 4 columns for the B. So in the output, we have 8 columns. So we use the VStack and HStack here, but what happens if we just use a stack, generic stack? And this means that we don't want to have in the vertical or horizontal. We just need to have them in another dimension. For example, here we have 2 arrays, and we call np.stack, and we get the shape of that. So in this case, we just add another dimension to the output, and then for each dimension we have a. For example, for the first dimension we have a, and then for the second row we have b in the output. So if we just call the stack not VStack or HStack, we are adding a new dimension to the output by the number of arrays that we are passing to the stack. Another way to combine two np.arrays concatenate, and then in this function we pass the number. In this function we pass the arrays that we want to have in the output, and then we can mention axes 0 or 1, and you can see the output is the same as this can generate the output same as VStack, and this can generate same output for HStack here. 6-4 for the first one and 3-8 for the second one. So they are same as VStack and HStack, but you can use concatenate here as a function in the Numpy. So we just introduce the function that we can combine arrays. But if you want to split some arrays, for example, if you want to split these 6 rows and 4 columns to 3 rows and 4 columns and 3 rows, another 3 rows and 4 columns, you can do that with same function that we have in the Numpy and the Numpy array. So we have another topic in this lecture which is the we need to have a copy of one array, for example, uh, one-dimensional array. How we can do that? We just need to copy the numbers that we have in one array. So this means that if, for example, we have a two-dimensional array, and we assign A to the B, right? So if we just check that B is A, this can generate the output is true. So B is equal to A in this case. So if we change the elements in the A, the elements that we have in the B also can change. So maybe we don't want to do that because we want to have, for example, change the value in the A, but without changing the value in the B. So in this case, we need to copy the numbers that we have in the first matrix, and then we, for example, here we call a function copy and parentheses for the first two-dimensional array, and then assign these to the B. So these can create a new copy of the A in the memory. So if we enter B is equal to A, this can generate a false, means that B is not equal to A. So in this case, the numbers that we have in the A and B are the same, but they have different location in the memory, and if you change one of them, the other one is the same as before. So because the content of the array are mutable, we often need to copy the contents of an array to avoid overwriting the original. So in most cases, you need to, if you want to copy of array, you need to use this function, which is dot copy parentheses. And there are some basic linear algebra that you can do that with Numpy. And note that we are using Numpy because Numpy is program is implemented in C, and we have lots of functions in the Numpy that they are so effective and can be computed effectively. So this is the big reason that we are using Numpy, because we can have access lots of functions without losing time. For example, for the basic linear algebra, you can get the dot product between two arrays, but calling np dot and passing to matrix to that. And also you can have other linear algebra function in the Numpy. For example, here we can have for singular value decomposition by calling SVD, or inverse, or trace, or outer. So all these functions can be available in the Numpy, and computing them by Numpy cannot be so time consuming and anymore, and lots of functions that implemented in the Numpy. So you just need to use them. And also Numpy have some function to load and save some arrays. into files. So for example, here we can call np.save, and we need to save an array to a file. So we need to pass a name for that file, and then comma, and then the array that we want to save on the file. So if you save that file, you can read that, or you can load that file by calling an np.load and the name of the file, which can be sometimes useful because you need to generate an array in your file, but you want to have access to this array in the future. So you just need to save that array, and then in the future you can load that array and then have some operation on that. And if you want to load or save text in the NumPy, also you can do that with two functions, load text and save text, to read and write file. And there is a character that separate each entries that you have in the text, which is delimiter, and in the default it's tab, because mostly we have no, not mostly, but maybe the entries in the file are separated by tab or a space or something like this, but we can define that or by passing this parameter to this function. So if we want to just save a text in the NumPy, we can call np.saveText txt, and then pass the number, the name of the text, and then the value that we want to save on that text, and then delimiter that, which is the comma here. And in the future, if you want to load that text, you just need to pass the number of the name of the text, and then comma as a delimiter. So this is the end of the today lecture, and if you have any question about the content of the lecture 4 or previous lectures, you can ask me by an email or post on the Piazza, and that's it. And have a good one. If you have any question, just let me know.